Integral test and p-series. Before we take a look at the integral test, we're going to notice that the infinite series, the sum from n equals 1 to infinity of 1 over n, is nothing more than a left Riemann sum for the integral from 1 to infinity of 1 over x dx. Let's take a look at this graphically. So here we have a graphical representation of the improper integral from 1 to infinity of 1 over x dx. So we have this area shaded here. If we were interested in approximating this area using rectangles, then with left endpoints defining the height, then we can look over here on the left. So here we're making each of our rectangles have a width of 1 and the heights defined by left endpoints. So in other words, this first rectangle has an area of base 1 times height 1, which is just 1, and the second rectangle has a base of 1 and a height of 1/2, because again we're substituting into 1 over n, so we have 1/2 and then a height of 1/3 multiplied by 1. So we can see that each of these rectangles has an area of 1, 1/2, 1/3, 1/4, and so on, and if we add all these up, then we obtain this infinite series. So we want to notice further from the graph that the sum from n equals 1 to infinity of 1 over n, the left Riemann sum, is greater than, there's more area, than the improper integral from 1 to infinity of 1 over x dx. Well, we know from our study of improper integrals that the integral from 1 to infinity of 1 over x dx diverges. And since the harmonic series, the sum of n equals 1 to infinity of 1 over n, is more area than something that we already know diverges, it too must diverge, as we already know. So we already know the harmonic series diverges. But now we know this by comparison. So by comparison, since the integral from 1 to infinity of 1 over x dx diverges, then the larger sum from n equals 1 to infinity of 1 over n must also diverge. So they have the same behavior. Now let's consider the infinite series, the sum from n equals 1 to infinity of 1 over n squared, which represents a left Riemann sum for the integral from 1 to infinity of 1 over x squared dx. If you use the nth term test for divergence on this series, what would that tell us? Well, the nth term test for divergence says to take the limit as n approaches infinity of the a sub n, or 1 over n squared, which gives us 0. So that's inconclusive. We're not sure whether this series converges or diverges. So let's go ahead and try that same thing and think about the fact that this series represents a left Riemann sum for the improper integral. So here's the improper integral. Looks very similar to 1 over x because 1 over x squared looks similar. So here's the actual area under the curve, and if we use a left Riemann sum approximation, this is what we have graphically. And we know from our study of improper integrals that the integral from 1 to infinity of 1 over x squared dx converges. Now the reason for this is because this is 1 over x to the p, and when the value of p is greater than 1, then we know the improper integral converges. But this doesn't really help us. So if this improper integral converges, but we have a series that's more area than that, the series 1 over n squared is more area, we don't know if our series converges or not. So we're going to do a little bit more analyzing. If we take a right Riemann sum instead for the improper integral from 1 to infinity of 1 over x squared dx, so over here we're using right-hand endpoints, then we're considering this series, starting at n equals 2 to infinity of 1 over n squared. Because notice that my first height is defined at the x value 2, and then 3, and then so on. So we're not using that value of 1, so we are considering a different infinite series. But the comparison works out. So by comparison, since the integral from 1 to infinity of 1 over x squared dx, that's this over here, we know this converges because 2 is greater than 1, so we know this converges. Well, then the smaller n equals 2 to infinity of 1 over n squared must also converge. But again, we're starting this one at 2 using that right Riemann sum. And we were ultimately trying to find out about the sum from n equals 1 to infinity of 1 over n squared. But we can think about it as substituting in 1, that's the first term. So if I substitute 1, 1 over 1 squared is 1. And then plus the remaining terms, n equals 2 to infinity of 1 over n squared. So since this series is equal to 1 plus this series that we know converges, if we know it converges to some finite number, that means adding 1 onto it must still converge. So we still have that the sum of n equals 1 to infinity of 1 over n squared converges. So this leads us to the formal integral test. The integral test. Let a sub n be a sequence of positive terms, and suppose that a sub n is equal to f of n, where f of x is continuous, positive, and eventually decreasing. Then, the sum from n equals big N to infinity of a sub n, and the integral from big N to infinity of f of x dx both converge or both diverge. In other words, the infinite series and the improper integral have the same behavior. Note, the integral test will tell us if a series converges or diverges, but it does not tell us what the series converges to. So basically, if we are trying to determine whether an infinite series converges or diverges, as long as that general term as a function of x is continuous, positive, and eventually decreasing, then we can evaluate the improper integral of that function, and then the two different things, the series and the integral, have the same behavior. They either both converge or they both diverge. As a corollary to the integral test, we obtain the following result about p-series. P-series test. The sum from n equals 1 to infinity of 1 over n to the p is called a p-series, where p is a real constant. A series of this form converges when p is greater than 1 and diverges when p is less than or equal to 1, similar to the conclusion for improper integrals of the same form. In this example, we want to determine, does the sum from n equals 1 to infinity of 2 over 5 n to the pi converge or diverge? Well, what we can do is we can take the 2 over 5 to the front of the infinite series so that we can clearly see that we're evaluating the sum from n equals 1 to infinity of a p-series, 1 over n to the pi. Since pi is greater than 1, we know from the p-series test that this infinite series converges. So we'd say, since pi is greater than 1, by the p-series test, the series converges. In the next example, we're going to use the integral test to determine if the following series converge or diverge, starting with the sum from n equals 1 to infinity of n times e to the negative n squared. I'm going to start by writing this as the sum from n equals 1 to infinity of n over e to the n squared. To apply the integral test, we need to make sure that as a function of x, we satisfy a few conditions. So we want to go ahead and start with, note, f of x, which equals x over e to the x squared, is first of all continuous, positive. So we know that it's positive because we're only evaluating this for n values greater than 1. So exponentials are always positive, and then if x is greater than 1, we're always positive. So f of x is continuous, positive, and decreasing for x values greater than or equal to 1 since, and now we actually have to verify this decreasing part. So we know that this is positive and we know that this is continuous because it's a quotient of two continuous functions and a composition of continuous functions. So we know all that, but we want to verify that it is decreasing. So to show that this function is decreasing, we're going to have to take its derivative. So since f prime of x is equal to, so the derivative here, we're going to have the bottom function, e to the x squared, times the derivative of the top function, 1, minus the top function x over the derivative of the bottom function is e to the x squared times 2x, all over e to the x squared squared, which is equal to, here in the numerator I can factor out an e to the x squared, and I'm left with 1 minus 2x squared over e to the x squared squared. Now here what I can see is that one copy of this is going to cancel out, so I have 1 minus 2x squared over e to the x squared. And if I substitute in values greater than 1 into x, so again the denominator is always positive, but 1 minus 2x squared, if I plug in numbers here, 1 minus 2 is already negative. So this quantity is going to be less than 0. So if we kind of read through this, we're saying no, f of x equals x over e to the x squared is continuous, positive, and decreasing for x values greater than 1, since my derivative, f prime of x, equals this function is less than 0, for x values greater than or equal to 1. So all of this just means I can apply the integral test. So let's go ahead and do so. We have the integral from 1 to infinity of x over e to the x squared dx, which becomes the limit as b approaches infinity of the integral from 1 to b of x over e to the x squared dx. This requires a u substitution of u equals x squared. Du is 2x dx, so 1/2 du is x dx. And we'll change our limits of integration, so u of 1 squared is 1, and u of b, well that's just b squared. So this becomes the limit as b approaches infinity of 1/2 the integral from 1 to b squared of du over e to the u. So we're going to have to rewrite this as the limit as b approaches infinity of 1/2 the integral from 1 to b squared of e to the negative u du. And then we will go ahead and find the antiderivative, which is negative e to the negative u, evaluated from 1 to b squared. And then we also have this 1/2 that's being multiplied, and we're still evaluating a limit at infinity. So what we have is the limit as b approaches infinity of negative 1/2 e to the negative b squared minus negative 1/2 e to the negative 1. And we want to take the limit as b approaches infinity here, so it might help if we think about this as the limit as b approaches infinity of negative 1 over 2 e to the b squared plus 1 over 2e. Because now, as b approaches infinity, this denominator is getting really big, so negative 1 over a really big number is 0. So this part goes to 0, so all I have left is 1 over 2e. So what does this tell us? Well, since the improper integral converged to 1 over 2e, we know that our infinite series converges. Now, we don't know that it converges to 1 over 2e, we just know that it converges. So we'd write, since the integral from 1 to infinity of x over e to the x squared dx converges, by the integral test, the series n equals 1 to infinity of n over e to the n squared also converges. We're going to use the integral test again on the sum from n equals 2 to infinity of 1 over n times natural log n squared. So again, we want to start by saying something like, note f of x, which is 1 over x times natural log of x squared, is continuous. So we definitely know this is a continuous function, again as a quotient and product and composition of a bunch of continuous functions. So is continuous, positive, so let's think about that for a second. So since we're substituting in values greater than 2, natural log x after 1, so if I think about the graph for a brief second of natural log x, it passes through 1, so 2 and beyond, I am positive, so I'm continuous, I'm positive, and decreasing for x values greater than or equal to 2, because now on this one I'm going to do my justification for decreasing a little different. It's a little bit easier, and the reason for that is because I have just a number in the numerator. So here, if I can guarantee that the next term is smaller, then I know that I have a decreasing function. So the reason is because if I have 1 over x and then natural log x squared, well, what I know is that the next term is plugging in x plus 1, because we are talking about a series here. So if I think about plugging in x plus 1, well then that's 1 over x plus 1, and then I have natural log of x plus 1 squared. So if I think about this, here I'm taking 1 out of this value, this number, and here I'm taking the same value, 1, from this value, which is bigger. So here that means the overall fraction on the left is bigger. So I'm taking 1 out of, let's say, 100, and here I'm taking 1 out of 101. So the fraction over here is going to be bigger. I'd rather have 1 over 100 than 1 out of 101. So I know that this is my nth term, and that's bigger than my n plus first term, so my sequence is decreasing, and my function representation is decreasing. So now I can apply the integral test. We'll have the integral from 2 to infinity of 1 over x natural log x squared dx, or the limit as b approaches infinity of the integral from 2 to b of 1 over x natural log x squared dx. So this is going to require a u substitution. I can see u is natural log x, and its derivative is right there, 1 over x. So I have u is natural log x, du is 1 over x dx. I'm going to change my limits of integration. U of 2 is natural log 2, and u of b is natural log b. So my limit is going to become the limit as b approaches infinity of the integral from natural log 2 to natural log b of 1 over u squared du. And now I have to take the antiderivative of this, so this is u to the negative 2, so I could think about this as u to the negative 2, so the antiderivative is u to the negative 1 over negative 1, or negative 1 over u, evaluated from ln2 to lnb, and then we're still going to have to evaluate the limit at infinity. So now I'm at the limit as b approaches infinity of negative 1 over natural log b minus negative 1 over natural log 2. So here these become pluses, and as b approaches infinity, negative 1 over ln b, well, ln b goes to infinity, so that goes to 0, and then I have 1 over ln2 left. So I have 1 over ln2 as my answer. Since this is a number, we know that the improper integral converges. So by the integral test, the infinite series converges as well. So we write, since the improper integral converges, by the integral test, the series also converges. But note that the infinite series doesn't necessarily converge to 1 over natural log 2, what the improper integral converged to. Here, let's use the integral test on the sum from n equals 1 to infinity of n over n squared plus 1. So we'll make sure we can apply the integral test. We'll say, note that f of x equals x over x squared plus 1 is a continuous function. It's actually continuous on all real numbers, so we don't have any domain issues here. So on this rational function, we're continuous everywhere. We're continuous, we are positive, so when we plug in values greater than 1, we are definitely going to be positive. And decreasing, so we're going to have to show this, and decreasing because, let's take the derivative now, because f prime of x is equal to the bottom function, or low, d high, the derivative of the top is 1, minus high, that's the top function x, d low, the derivative of the bottom is 2x, over the bottom squared, low squared. So x squared plus 1 squared, well that's equal to, we're going to have x squared plus 1 minus 2x squared over x squared plus 1 squared, and that's 1 minus x squared over x squared plus 1 squared. So we have to justify, well, the derivative is actually going to be negative, so less than 0, if our x values are greater than 1. If our x values are greater than 1. So it's eventually decreasing because right at 1 I'm equal to 0. But if I start substituting in numbers greater than 1, 2, 3, 4, etc., then I have 1 minus some number bigger than 1, so this is going to be negative on top. And the bottom is always positive. So we do have the conditions to apply the integral test, so let's apply it. So we're going to have the integral from 1 to infinity of x over x squared plus 1 dx is equal to the limit as b approaches infinity, the integral from 1 to b of x over x squared plus 1 dx. And this is a u substitution problem, so u will be x squared plus 1. Du will be 2x dx. We only need an x dx, so 1/2 du is x dx. And then we'll change our limits of integration. So u of 1, 1 squared plus 1 is 2, u of 1 is 2. U of b is b squared plus 1. So we have the limit as b approaches infinity of 1/2 the integral from 2 to b squared plus 1 of du over u. So we can go ahead and take the antiderivative of that. We get the integral, or the limit, as b approaches infinity, of 1/2 the natural log of the absolute value of u evaluated from 2 to b squared plus 1. Well, if I substitute in now my limits of integration, I have 1/2 the natural log of b squared plus 1 minus 1/2 the natural log of 2. Well, as b approaches infinity, here this is the only term involving b. This inside is going to go to infinity, and natural log as I approach infinity is infinity. So this part is infinity, so this whole limit does not exist. And so this improper integral diverges. So since the improper integral diverges, that means that the corresponding series also diverges by the integral test. And we write, Since the improper integral from 1 to infinity of x over x squared plus 1 dx diverges, by the integral test, the infinite series has the same behavior. So the sum n equals 1 to infinity of n over n squared plus 1 also diverges. So as you can see, the integral test is definitely going to require us to know how to evaluate integrals. That is obviously a key part of applying it, in addition to making sure that we have the right conditions for being able to apply it. So we need our function representation of the general term of the sequence to meet the requirements of being continuous, positive, and then eventually a decreasing function. So now, just circling back, finding the interval of convergence for a power series, if we have Cn is a constant, we can apply the geometric series test to find a complete interval of convergence. But if Cn was a function of n, we have to apply the ratio or root test to find an incomplete interval of convergence. It's incomplete because we must test the endpoints for convergence. But now we have this test, the integral test, to help us test for endpoints. So let's try an example of finding a complete interval of convergence. So in this example, we want to find the interval of convergence for the sum of n equals 2 to infinity of x to the 2n over n times natural log n squared. So we know that a series converges if the ratio test applied to it is less than 1. So we're going to start by finding the radius of convergence, so the limit as n approaches infinity of the absolute value of x to the, here we're going to plug n plus 1, so we're applying the ratio test. We're going to plug in n plus 1 into n, so we get x to the 2n plus 2 over, we're going to have n plus 1, and then natural log of n plus 1 squared times the reciprocal, because the ratio test says a sub n plus 1 over a sub n. Well, instead of dividing by a sub n, we'll multiply by the reciprocal, n times natural log of n squared over x to the 2n. But this time, we know that an infinite series, if the limit of the ratio test is less than 1, then we know it converges. So we want to find the interval of convergence. So instead, we're going to end up trying to solve here for x. So as n approaches infinity, let's see all the quantities that have n involved here. So we have n, and then an n plus 1. So as n approaches infinity, we can start to see, well, that part's going to become 1. And then here we have natural log of n squared, natural log of n plus 1 squared. So that as well is going to go to 1 as n approaches infinity, because we still basically just have natural log n, each of those is squared. So then all we're really going to have left is this x to the 2n plus 2 and this x to the 2n part. So in other words, we have the limit as n approaches infinity of x to the 2n times x squared, if I'm splitting it up, and then x to the 2n on the bottom, and then the n over n plus 1 part, that's going to go to 1, the natural log of n squared, and the natural log of n plus 1 squared, all that's going to go to 1. So here, if I evaluate the limit, then all I'm going to have left, because x to the 2n and x to the 2n cancel, I'm just going to have the absolute value of x squared is less than 1. So I've evaluated the limit of these pieces. Remember, all of this went to 1. So all that's left is x squared in absolute value bars. Well, as an interval, so here the solution set to this is going to be -1 is less than x is less than 1. So this right now is my interval of convergence without testing the endpoint. So I have to see, well, what happens right at -1 and what happens at 1. So my radius of convergence, in other words, is 1 if this thing is centered at 0, but I need to determine what happens at each endpoint. So let's go ahead and test it out. So we're going to check what happens when x is equal to -1. So we'll have the sum of n equals 2 to infinity. We're plugging a -1 in right here into x. So -1 to the 2n is what we're doing, and then over n times natural log of n squared. Well, if I take negative and square it, then that just becomes positive. So that's just a positive 1 on the top. The sum of n equals 2 to infinity of 1 over n natural log of n squared. And this should look familiar. We actually already went ahead and determined whether or not this converge or diverge in an example from above. And we saw that this converges. So this converges by the integral test. And I'm just going to go ahead and put C above. So we actually did the work for that there. So now here we know that -1 is included in the interval of convergence. So we know that we can go ahead and put less than or equal to next to the -1. And if we check what happens at x equals +1, well, the same thing is going to happen because it's the same exact series. If I plug in a 1 right here into this x, 1 to the anything, in this case it's just going to be 1. So we're going to have the sum of n equals 2 to infinity of, again, 1 over n natural log n squared. And again, we already know this converges C above, right, by the integral test. So that means that now I can also put a less than or equal to sign next to 1. So my complete interval of convergence is everything from -1 to 1, including -1 and 1. So just applying the ratio test gave me an incomplete interval of convergence, or really just the radius of convergence, and we needed to figure out what happened at the endpoints using, in this case, the integral test.